Okay, so yesterday we started talking about what a limit was. We started talking about that notation. And so all of this slide talks about some slight new notation, but we had actually used some of this notation last year. If we approach a, some value on the graph, and we go to infinity, we have actually approached a vertical asymptote. And as we approach that vertical asymptote, wherever it is at some value a, we are going upward. So that's what that notation is. So if we approach a vertical asymptote, we will either head to positive infinity if we're going upward, or this one right here, we still got that asymptote, but we're going downward. So that's the main thing here. This means we've approached the vertical asymptote and we're going upward. This one means we've reached a vertical asymptote and we are going downward. So that's what all that mumbo jumbo language is. So there's a lot of stuff there, but those are the main things that we need to know. Now, there's a problem if you see that we are not approaching it from the left or the right. Let's draw a little picture. This means, and I'll zoom in a little bit, at A, that's so, it didn't hit A, but you know, both sides are going upward. Okay, so let me fix the picture slightly. Gosh darn it. Anyway, at some value A, you're going upward. The bottom one, at some value A, both sides have to go downward. Remember, for a limit to exist from the left and from the right, we have to be going in the same direction. So for them to say that the limit is infinity, both sides have to go up. For them to say that the limit is negative infinity, both sides are going down. Now, often when it comes to a vertical asymptote, one side will go up and one side will go down. In that particular case, the left side might be positive infinity and the right side might be negative infinity, but at that point it won't exist. So you have to be concerned about, are we going in the same direction from both sides? Okay, but this is just fancy terms for what's happening for our vertical asymptotes. So if we get an answer to a limit as positive or negative infinity, we have hit a vertical asymptote in the graph. That's the main thing to remember. So let's look at this notation. There are 6 cases where the vertical asymptote at A has an answer of positive or negative infinity. Do you see how this has that little negative, like exponent? That means from the left. We are going up. So from the left, we are going up, and it's really referring to that little side as we approach that vertical asymptote. In B, we are coming in from the right, and we are going up. So they're talking about this end right here, okay? So that's a left or right-sided limit that is positive infinity. Those functions don't have the opposite side. This doesn't have a right side. This one doesn't have a left side. So these wouldn't exist exactly at that point. So be careful about that. These ones are going down from the left and right. So this is from the left. From the left side of A, we are going down, but we have hit a vertical asymptote. from the right, we are going up. So we have hit a vertical asymptote, or not up, I'm sorry. We're still going down. So that negative infinity just says that we are going down from that side. So the only way we can get a true limit of infinity is if both sides go up. So at A, both are up. At A, or as we approach A, both go down. So just be careful about the notation of this. Similar to what we did yesterday, it's not going to be super hard. It's just a little weird, and the notation's a little strange. That's my takeaway from this, okay? So now let's actually look at an example of where we can apply some of this information, okay? Do we have any questions about the graphs we've seen so far? Okay. So let's look at this example. So again, because the way this graph paper is, I'm going to kind of highlight the X and Y axis just to make them a little pop and clear. Okay. I'm also going to highlight or draw a graph where I believe that I see a vertical asymptote. So I'm going to put a vertical asymptote there. It's just a highlighted greenish area in there and there. And then right above the graph, I'm going to write what the vertical asymptotes are. So I'm going to do E before I do anything else, okay? I'm going to do E first. So there's a vertical asymptote. The equation of a vertical asymptote is always x equals a number. So at x equals -3, at x equals +2, and at x equals +5. So just put those right on the graph at the top or bottom of the vertical asymptote, okay? Hi. Oh, goodness gracious. That's a lot of stuff, isn't it? A lot of stuff. Are they heavy? Not too bad. Okay, if you could just put them on this back table for me, okay? Okay. So now let's do the top stuff so we can have, just a sense of how do we note that we have hit a vertical asymptote, okay? So the first one there says we are approaching 2. So let's go ahead and let's focus on this area right here. As we go to the left, we're going down. As we go to the right, we're going down. So where are we heading toward? Negative infinity, right? Okay. So the answer to that first one there is negative infinity. Okay. Now let's do B. So we're looking at 5. As we head to the left, we're going up. As we head from the right, we're going up. Where are we heading toward? Positive infinity. And you don't have to put the positive notation there. You can just put the infinity, whatever you want. Okay. Now, let's look at C. See how they said we are coming in from the left. So we are talking about that side right there. Where are we heading? Down, negative infinity. But let's look at D. What's that notation telling us that we're doing? We're coming in from the right. So we're going here. So where are we heading that time? Positive infinity. So if the question just said, what is the limit as x approaches -3 of r of x, what would we say? The left side's going down, the right side's going up. What do we say about limits when the sides don't match? Does not exist. So you can put DNE or you can put the null set. Okay? So that's just how a vertical asymptote is noted on the graphs. Do we have any questions about example 4? Any questions about example 4? Okay. Now, these ones, I've said, I think, to you before, when we're learning math, addition's easier than subtraction, right? It's just easier. It's still, to this day, it's probably easier. Isn't multiplication easier than division usually? Well, going forwards in math is usually easier than going backwards. So when we're given a graph, pulling out the information is pretty good. But when we're asked to give the graph that fits this information, it gets harder. So this is an example where it becomes a little more difficult. Okay, so let's take a look at example 5. Now, what I tend to do for problems like this is I make little teeny portions of the graph and then connect it to make it look more like a graph when I'm all done. You'll see what I mean in a minute. So the first thing says, as I approach 0 from the left, I have to be going to 1. So that's what you should read in your head. As I approach 0 from the left, I better be going to a height of 1. So what you want to do, and let's make, just so I have more room, let's make that 1 and 2 and so on. I'm going to skip like little sections. So every other one. So I guess I'm counting by halves, maybe. Just so that my graph paper will look a little nicer for you. Okay. So as we are coming in from the left of 0, we should be heading to a height of 1. So I am just going to put an open circle because I don't know what's really happening there. And I'm just going to make a little tail on the left. Says, oh, I'm heading to 1. Sure. On the left side, I'm heading to 1. I don't know if I reach it, but I'm heading there. Okay. Now let's come in from the right. I should be heading to -1. So down here at -1, make a little tail on the right. I don't know where that tail's going to go. I might even have to erase it and make the tail go down instead of up, but we're just getting a little piece ready. Okay. Now we're heading all of this. Oh, see here where it says f of 0 is undefined. So we get to leave it open. Okay. Now all of these pieces next are about 2. From the left side of 2, I'm heading to 0. So I am going to make a little open circle here, and I am going to go in from the I don't know, I'm going to put a little tail over there. Okay. And now I'm going to do this one. From the right of 2, I am heading to a height of 1. Again, I always make an open circle because I don't know how it's defined. But it says in this little spot that at f of 2, I'm allowed to color in that spot. Okay. So now let's make it look a little more like a graph. That looks like a mess of things. So let's just, well, we'll put a little tail there. We'll make it look like a graph over there. We can connect these two. Your graph and my graph might look different. You might have gone like this. Are you still approaching a height of 1 from the left? Yeah. Your graphs might not have connected. That's okay. Do I still have a piece here and a piece here? Yeah. I went up, you might have went down. You might have just had a little section right there. So this is where your graph and my graphs might look a little different, but we might both have a perfectly good example of how that happens. I would always suggest, once you have your graph done, going back and looking, did I get all the markers they said? So let's look. Am I approaching 1 from the left of 0? Yep. Am I approaching -1 from the right? Yep. Is f of 0 undefined? Yep, nothing there. As I approach 2 from the left, am I heading to 0? Yes. 2 to the right, am I heading to 1? Yes. Is f of 2 equal to 1? Yes. My graph works. So make your graph, make it look pretty, then read the instructions one more time. Did I hit all the markers that they wanted of me? Again, your graph, my graph, we might look very different. Everybody good with that? Okay. Let's take a look at example 6. Now, for the very first time, we are just asked about a limit when a function is given to us, okay? Last year, I tried to start preparing you for limits without you maybe realizing I was preparing you for limits, you know, because I'm good at this stuff. Let's think about what I used to tell you. If we found a limit, I would tell you that the math should be a number over 0. Remember, I did tell you that. If you find a vertical asymptote, you should get, the math should be a number over 0. Well, a vertical asymptote algebraically should always be some number over 0. And that's going to happen with these next examples. Now, A says that we are approaching 5 from the left. Now, if you're great at graphing, you can graph it, look at what's happening to the left. That's going to answer the question for you. But many times we're better at algebra quicker than we are at graphing. Most people are. You can do the algebra a little quicker than you can graph. So what I would do first is I would try something we're going to refer to as direct substitution. Substitute the number in and see what's it telling you. If I plug in 5, don't worry about the little to the left thing, but if I plug in 5, I get 6 over 5 minus 5, or 6 over 0. Guess what? It's telling me I just hit a vertical asymptote. It is an undefined value in the graph. So give me a number that is a tenth away, but on the left of 5. What is to the left of 5, but a tenth away? Yes. Almost? No, you're going the opposite way. 4.9 is what you're thinking. Okay, so we want 4.9. We want a number just to the left of 5, but a tenth away. So what I want you to do is you're going to do what's called a test case. And we're going to plug in 4.9 because it's to the left, just close enough away. It's going to give us the information we're looking for. If we plug in 4.9, we get 6 over 4.9 minus 5. We don't really have to do any more math. We have to do some logic. We have to do some math. But is 6 a positive number? Is 4.9 minus 5 a positive or a negative number? Negative. What's a positive divided by a negative? The answer is negative infinity. Now, why? Because no matter what number that I put in that's to the left of 5, close to it, I am always going to get a negative number. The closer to 5 it is, the more negative it's going to be. And that's going to happen again and again and again and again and again. So the answer to A is negative infinity. If you were to draw the graph, let's draw the graph. There's a vertical asymptote there. The left side's going down. The right side's going up. What's the left side doing? Going to negative infinity. So the algebra and the graph should always coincide. If it doesn't, one of them is wrong. They should go together. Okay. Now let's do the same thing for part 2. You always try direct substitution. What does that number tell me? What does the number 0 tell me? Well, 0 tells me I get -1 over 0, which tells me I just found a vertical asymptote. But did this one specify left or right? No. So this one has to have 2 test cases. To the left of 0, I'm going to plug in negative 0.1. To the right of 0, I'm going to plug in positive 0.1. If I get a positive both times, my answer is positive infinity. If I get a negative both times, the answer is negative infinity. If I get one that's positive and one that's negative, one's going up, one's going down, there isn't a good answer. Okay, so let's plug in our test case for negative 0.1. Negative 0.1 minus 1 is a negative number. That's all I really care about. I don't care about the value of it. If I plug in negative 0.1 in the bottom, I get a negative 0.1 squared times negative 0.1 plus 2. That is going to be a positive because the squared's a positive. Negative 0.1 plus 2 is a positive. That's a positive. A negative divided by positive is negative. So that side's going to negative infinity. Now let's plug in positive 0.1. I get 0.1 minus 1, which is a negative. That's all I care about. If I plug in 0.1 down at the bottom, I get a positive. A negative divided by positive is a negative. Are they both going the same direction? Yes. Now you can actually get a number there, throw it in a calculator. You're going to get a negative for the first one, negative for the second one. If they're both negative, your answer is negative infinity. If they're both positive, the answer is positive infinity. If they don't match, it doesn't exist. Now let's take a look at C. I really don't want to do C, but I'm going to do C anyway. I know that's radians, 180 degrees from the left. But let's just talk about 180 degrees pi for a minute. Cosecant is the flip of the sine. The sine of 180 is 0. I can't do 1 over 0. So I found a vertical asymptote. The cosecants, you might recall, are vertical asymptote, like parabola-like thing going up, vertical asymptote, parabola thing going down, vertical asymptote, parabola up, vertical asymptote. It's not really a parabola, but it's a squished parabola in between those lines. But so we should expect cosecant and secant have vertical asymptotes, tangent and cotangent have vertical asymptotes, sine and cosine do not. Okay, anyway, we found one, but we only need to plug in things to the left. We need to be really close to pi. So I'm not going to use I'm going to use degrees. And I'm just going to throw it into the calculator and see if it's positive or negative. Is my parabola going down? So the answer would be negative infinity. Or is my parabola going up? So it'd be positive infinity. I don't know off the top of my head. Well, I could really think about it. Sine just above 180 is a positive value, right? So I'm assuming the answer is going to be positive infinity, but let me show you how you can do it. If you do a test case, make sure your calculator is in degree mode, and let's just make it 179 degrees, because to the left of it would be just before we hit it. So just make sure it's in degree mode. If you do the sine of 179, that's really all you need, because the sine and the cosecant are reciprocals. So if one is positive, the other is positive, or vice versa. The sine of 179 is positive 0.17. So the cosecant of 179 is positive 57.3. So it is positive infinity. So the answer is positive infinity. And then if you graphed any of these things in Desmos, you can test, is there a vertical asymptote at that spot? Yes, there will be. Is it going down at that spot? Is it going up at that spot from that side? And you should be able to look at that. So we will explore more the algebra of these things as we go. So that's very new and very weird, and we will keep talking about it as we go. Those are kind of the weirdest ones we've seen so far. Any questions about example 6? Okay. So that leads you to this. So you have a nice chunk of time. Please get started with this assignment right now, and I'll help you with whatever. I believe it's due on Sunday. So it's the odds 1 to 9, 13, 15, and 29 to 37. So there you go.